Hi, in this video I'm going to show you how to integrate a peripheral device using I2C bus to Raspberry Pi Pico. So as you can see it here, my setup is I have a chip MAX30105, which is a sensor with multiple capabilities. It also has a onboard temperature sensor, and that's what we are going to use today. Apart from that, you will see here I have the UART output connected to a Raspberry Pi. So Raspberry Pi can show a serial output on the screen. The connection is simple. So the first two pins are used for default UART, which we can see it here. Just give me a minute, second. I'll switch. So these are the Raspberry Pi Pico pinouts. So the first two pins, UART 0 and UART 0 TX and RX, are the default UART pins on Raspberry Pi Pico. And similarly, the I2C default port is GP4 and GP5. So in my example, I'm using UART 0 for output, which is connected to Raspberry Pi, and then I'm going to print using Minicon on Raspberry Pi. And my peripheral is connected to I2C default port, which is GP4 and GP5. Apart from that, the power is coming from 3.3, so 36 pin, physical pin 36, and ground from 38. And then since to load a firmware, every time we have to power cycle the Pico, and then we have to connect. So instead doing that, I have connected the run pin, which is the physical pin 30, and then with the button to make it low to connect to ground. So what happens is whenever I press the button, this pin is brought to ground, and then the Pico will reset itself. So I have to hold this button and then press the reset button. So that's my setup, which you can see it here. So that's my green, the first green and blue. Those are the two UART pins which are connected to here. This one is going to Raspberry Pi UART port, and from the other side, the black and red is a power and a ground, and GPO 4 and 5 is here. They are brought to the peripheral and connected to a peripheral SLC and STA pins, and the power is from that one. And then the run pin, which is here, the yellow pin, is connected with the switch here, which brings it to on press it will bring it to ground, and then it will reset the Pico. And I also have two LEDs connected to pin 18 and pin 19 through a register. So that's all I have. These two cables are coming from Raspberry Pi. Raspberry Pi also has a I2C bus, so instead using Pico, if I want to directly use Raspberry Pi, I could do it. Just I have to switch from here, these two, red and the green and orange, and connect to here, which is coming from Raspberry Pi, and then I can use the same peripheral through Raspberry Pi. So that's my setup, hardware setup. Now on the software part, I have already created a project here, and this project is generated using if I show you here, the Pico project generator. So Pico project generator, which is the utility to generate projects, and this generates this folder structure. It creates a base files, and it gives a startup. So here you can select what kind of device you want to program. You can also select whether you want output over UART or USB, which you can change it in the CMake file. And then what type of language you want to use. You want to use a plain C, or you want to use C++. Also, you have option to select the VS Code to create the VS Code project, and then run build after generate. So these are the parameters which will create in the project. So just giving a name and selecting these options will will generate a project, which I have opened it here. So this project has let me send this to 3. Okay, so the project structure is fairly simple. It has the VS Code specific folder .vs code, which has a VS Code settings. Then the CMake list is generated from the Pico project generator. The demo I2C.cpp is also generated by the project generator. So whatever you see here is generated by the project except the upload.sh. I'm using Arch Linux, and I don't use the auto mount for the devices, USB devices. So I actually use a shell script to mount and to upload the file. So that's why we have this sh, which I generated. And in the project, so I have declared a few constants before starting the project, because they will be a lot easier to just use them during the coding. Now the first thing is in a main function, and this will be generated by the project generator. So if you are selecting project with I2C, then it will create the port as a default port, and then it will also create these entries. But remember, the project generator doesn't use GPO 4 and 5, it uses 7 and 8. So that is something you need to change. So I changed it here by using a constant as a default I2C SDA pin, which is 4 and 5. So basically, instead using defined, you use the default. Then I set them as GPO. Okay, so these are the LEDs which I showed you earlier, so we don't need them, so I'm gonna just remove them. And then we set their pull-up registers to activate the I2C pins. So I'm saying pull-up SDA and SLC. So this one is supposed to be SLC. I2 default SLC pin. So these we activate the functions, and then we activate the pull-up registers. Now the next thing is this is a while loop where while it generated with the it was a printf. I was testing something, so that's the while loop. So let's get rid of that and format. We don't need that either. It's good. Okay, good. Format. Okay, so the base program is ready. Now if I let's take a look at the I2C, what I2C protocol is. So I2C is a short form for inter-integrated circuits. It is a two-wire protocol where two wires are connected with the peripherals, and then they communicate over 2 wires using the I2C protocol. So, and one acts as a master, and the others, they act as a slave, and we could use many devices in the circuit. So that's the I2C. You can read, there is tons of explanation on internet. Now the next thing we need is the data sheet for the I2C device. So in our case, it's MAX30105. So I just open the data sheet for the device, and in the data sheet we need to look at the instructions. So if we go down, this is the device which has LEDs and sensors. These are the register maps and descriptions which we will be needing it for for us to read information from the device or to use the device. So this is very important to have. So that's the data sheet. Now going back, so to start with, the first thing is, in any I2C peripherals, first thing we need to do is we need to get the device ID, or some cases we have to reset the device. So in this case, this has a reset. So again, I'll be keep switching between the datasheet and the VS Code. So here, if we see, there is a mode configuration which has a reset, which is on B6. So we have to send the register address as 09, and then the reset address, which is BF, hexadecimal BF. So 40, because when it's a B6, which is a 40. So when we send this, the device will get resetted, and once it resets, it will confirm by returning 0F. So let's get started writing first as a reset. So we'll remove the printf, reset device. So like we said, we need a variable with int 8t, let's say reset, which is the 2-byte array. So we'll say reset 0, which will be the address, and I have defined it in here, this one, reset. So MAX30105 reset. So let's go reset 30105 underscore reset. That's our first, and then the second reset byte is for the value. So that would be this is the mode config, and this is the reset. So if we take a look here, basically it says what register. So our register is the mode config, which is 09 hexadecimal, and then the reset is on B6, which is 40. So that is what we did it here. Now once we have these variables, we have to pass this to I2C write blocking. The first parameter is the I2C port, which is the default we have chosen, and the address, so our device address, which I have defined it here, which is a 057, and then we pass our arguments, which is a reset, it's a 2-byte, and then true, do not block, keep the blocking, and then we will read back the value. So read until we have a response. So what we are gonna read is I2C read blocking, I2C default, I2C default, again address, and then we'll read state, it's a 1-byte, and then we'll keep the lock. So I did not declare the reset, so let's declare it again. Reset state, and then we can use the reset state here. Reset state. Okay, so we have reset state, it's a single byte. Okay, then we have to check if the reset state 1-byte return value 0F, which means it is successfully reset. So if that is the case, then we break the loop, else we'll just keep looking for that reset confirmation, and we will only break the loop when it is confirmed that the device has been reset. And then we will add a sleep 1 millisecond delay. So by now the device should be should be able to reset itself. So let's give a try. So let's add printf here, device successfully completed reset sequence. Okay, so okay, semicolon. Okay, so with this code we should have our device reset sequence complete. Now for this purpose I'm gonna turn on Raspberry Pi. I did not turn it on, so let's give a second. Then we'll connect to Raspberry Pi for the UART. We could check it here also, but I prefer to have a dedicated UART connected. So let's give a second. Meanwhile, we can build this project. So let's build. Exit code 0, that means it's successfully built. Now I haven't connected the device, so let me connect my Pico, and then we'll go to, okay, this is frozen, so let's check here. So I have connected my Pico. I'm gonna put it in a disk mode by holding boot select and pressing a button which is connected to the run pin. This should put it in the disk mode. Okay, STB1 is the device. So let's go to projects and demo I2C and build. So first thing, we have to mount this device because I don't have like auto mount, and I prefer to do it manually. So STB1. Let me increase the font. So mount STB1 to Pico. Okay, and then copy demo uf2 file to Pico, sync and unmount. Okay, so my Raspberry Pi is up. Let me go to a new session here. Pi add Raspberry Pi. Again, the screen. Okay, so here I will run the minicom. Okay, so the device ran very fast, and as you can see it on the screen, device successfully completed reset sequence. So our first part is completed. We have a device which has completed a reset sequence. Now the whole purpose of this device integration is to read the temperature, the chip temperature. There are multiple sensors on the chip, and I'm not going to code all of them for now. So it's just first starting point is to get the temperature from the chip. So the reset sequence is complete. Now we can start getting the temperature. First, okay, let's get the device ID, which we could have done first. So again, we can verify the device by get device ID. Again, that is here. So if we go down in the data sheet, here it says the part ID, which is 015. So this we can verify by writing a few more lines. So as usual, we need another variable for chip ID single byte, and we will be calling src write blocking src default, then 30105 address, and then we will be passing the part ID directly instead defining a variable. MAX30105 is the part ID. This part ID is defined, so let me show you where this is. Go up. So part ID is 0FF, and if we go on a data sheet, the register is 0FF. So that's what we did. I already declared that as a constant, so I'm just passing that part ID here, and then 1 and true. So we have our write blocking, and in a Raspberry Pi Pico you cannot just read, you have to write something and then you have to read it back. So it's always the operation is to write and read, write and read. So we are writing the part ID. So basically we're telling the peripheral to reply part ID. Since we wrote that, now we'll read it. Blocking I2C default port MAX30105 30105 address, and then we'll get the chip ID 1, and we will release the control after getting the part ID. Once we have part ID, we can print the part ID using printf. So the device ID, it's a hexadecimal value, so we'll have 0x %02 x, and let's add a new line, comma, chip ID and 0 and semicolon. So basically we're saying print my hexadecimal value for my chip ID, which is written by the device as a chip ID here. So let's save, build, and then we do the same thing. I will reset the device. Okay, give a second, mount, copy, sync, and mount. Go to the port here. This is on the UART port, so let me reset, and now it prints out device ID is 05. Let me reset one more time. Okay, so it says device ID is 015, device successfully completed reset sequence. So far we are reading the part ID register, and we also configured our device to have where is it? We also configure our device to reset itself on initial boot. So two things are done. Now the next thing is let's start with the get chip temperature. Now this is a little complicated part because let's go to the data sheet here. So to read the temperature, down here we have die temperatures. So there are different registers. We have the die temperature in integer, we have die temperature in fraction, there's a die temperature config, so we have to enable the temperature and then we will be able to read it. But to have die temperature mode activated, we have to set few interrupts. So we have, if we see it here, our die temperature is on interrupt status 2. When it sets ready, that means we are the peripheral is ready to send the die temperature, and interrupt enable 2 is to enable the die temperature. So first we enable it, then we check the status, and then we go fetch the die temperature in integer and a fraction. So this we have to write in a multiple steps. So first thing, we will enable the interrupt. So that's the first thing here. Interrupt enable 2, die temperature ready enable. No, first we will enable, then config, and then we'll check the interrupt state, and then we will read the temperature. So let's get started. First we'll define init 8. We need interrupt enable, so enable int enable 2, because this is a second interrupt we saw. We'll have a 2 byte because we have to send the register address and the register value. So interrupt enable 2, the first byte register address is MAX30105. I think it's here. Int enable, so that one, and int enable 2. This is the temperature ready enable, this one, die temperature ready enable. This is also defined. So first we pass the address and then the bit value. So back here, MAX30105, this one, enable, and then we need another variable for config. So die temp config. Again, this is two value array. So die temp config 0. The first is the die temp config, that one. And the next one is so if we go here, die temp config, that one, that's the register, and this is the value, which is basically the hexadecimal 01. So I think I did not declare this value anywhere here. We can use this one, but it will be misguiding. So let's put it directly in the in here. So that would be 0x0 first bit. Now we have those. Then we need two more variables to get these values. So int 8. First we will get the interrupt status. So int state 2, which is again 1 byte, and int 8, the die temp, again 1 byte. Okay, so now we have all the variables. Now let's send the this information. So I2C write blocking, I2C default, and we need to pass the first we enable. So we are gonna send the enable interrupt. So int enable 2, it's a 2 byte, and keep the lock. I2C write blocking. Now next we need to send I2C default, the die temp config. Again, this is a 2 by 2, so true. So far we have okay, so we are missing the address. That would be MAX30105 address, comma, and enable to. So that's why we see the error here again. Okay, so we are good. So we send the interrupt, then we send the die temperature config. Now we will do the while loop and we will check whether the peripheral is ready or not. So while true, we will check the value if my int stat, but we did not read it yet. Okay, so I need to hold on. Let's park this beside. So we wrote, okay, we can read in the loop to get the value, each value. So I2C, first write, blocking, I2C default, and then MAX30105 address, int stat, so that we can pass it directly. I have already defined a variable, so M30105, let's go int stat 2, this is 1 byte, and then true. So this is to get the interrupt status, second interrupt status, and now we will read a value for the interrupt. So this would be I2C default 30105 address, and then we have a variable int stat2, which is 1 byte, and then keep the log true. Okay, so now we have a value which we can check, verify here. Hold on. Okay, so we can verify that value here, int stat2, the first byte, and bit operation and MAX. I have defined a variable to check a value when it is ready, ready enable. If that is returned by the device, which should be 0. If this is the case, that means the interrupt return is ready. So basically the peripheral is ready to send the value. So we break that loop, and then let's add a delay, another delay here. So we broke the while loop, and then here we can read the temperature. I2C write blocking, I2C default, MAX30105 address. We need to read the die temperature. Again, I have a variable declared 1030 die temp, so it should be die temp. Let's see, where is it? Die temp integer. So that's the integer value we will be reading. It's a 1 byte, and then true, and that's it. We are passing it as a reference, so address reference, so that would be reference to memory. I2C read blocking, I2C default, again the address, device address, and we will be reading the actual die temperature. It's a 1 byte, and then we will be releasing the device after reading. Okay, So now, so by now we have a hexadecimal value for the die temperature. Now I'm not really comfortable with C, so I'm gonna copy something to convert this value into integer and print it. So this basically converts the temperature into an integer value, and then we print it and then sleep 1 millisecond. Now we could do this in a loop, so it will keep reading the temperature and printing it on the console. So let's try to build and see what happens. So there are no issues here. Let's go to the where was it? Here. I'll put my device in again boot select mode. Okay, let's give up a second. Mount. Okay, copy, sync, you mount. We should have here. Okay, reset. Okay, so for some reason it did not is not reading the temperature. Let's see. First of all, I have this reset. After reset sequence, we need carriage return. So /n. Now maybe here. So we are reading it here. We read and then we should be releasing the device. Okay, build, boot select again. Mount, copy, sync, you mount, 4, and there we have. So we have a die temperature now. If I reset, it will give me the temperature. Let me put a finger on it and then reset. It will start increasing slowly. So on every rerun, it will change temperature. Well, it's not drastic, but still there's a change. Now I removed my finger, and if I reset, it should go back to 28 and 27, which was the original. It will take time because it's warm here right now. So let's wait a few seconds. Yeah, there we have. So now temperature is back to 28, and that's all. So what we did now is we basically wrote the I2C kind of a driver for the MAX30105 to get the die temperature. Now this peripheral has many features. It also has the oximeter. It also detects the pulse. It also has a presence sensor, which I'm going to write drivers for. So this is just the starting, and I wanted to share a basic I2C programming. So let me know if you have any questions, suggestions down below in the comments. Thank you.